Okay, so welcome to 772, numerical analysis for computational science. So let's get all the course nitty gritty out of the way. Okay, so all right, so here we have. Yeah, yeah. Because some of you are in multiple classes with me, so you're gonna get so many of these look-alike documents. Okay, now. All right. Actually, I have one second. I need to run to my office real quick and get the textbook. Okay, so this is a textbook. So by Sully and Mayers. Actually met Sully at a conference once. And this book actually is available in, hopefully it's still available in Scribd, if any of you are familiar with that site. And might actually be able to get a full download of it. All right, I have a download of it too. So if any of you bought it already,
I did just got a hard copy, but I have a PDF too, if anybody needs it, so I need it.
okay, well, yeah. All right, so I can make it available. So you have a PDF also? Okay.
I've used this book before.
Oh, okay. Oh, you read it at your previous school? Okay, yeah.
We used it for like 460 and 461.
Ah, okay.
Didn't we use it for 460 and 461?
No.
I think I just started with science.
Yeah. So, so the funny thing is about this book is it's just 772. So for those of you who have taken 460 or 560, as far as how this class is distinguished from that one, this one's more hardcore theoretical. If you think of a typical undergrad numerical analysis class as one where you're like learning how to drive a car and maybe do some basic maintenance things like swapping out some bulbs or changing your own oil. This is a class where we take the entire car apart and learn how to put it back together again. So there's less of a focus on like the coding aspects of it and more about where methods come from, why they work or don't work, and so on. So the textbook and therefore a lot of the problems are going to be pretty proof intensive. And so when I got this book, it's like and saw what it was like for the first time I was going to teach this class, I'm like, wow, this is hardcore stuff. I like this. And then I look at a preface and I find that this book is aimed for undergrads. Now, to give context, Sully is a professor at Oxford, the one in England, not Ole Miss. And Oxford is basically the mecca of numerical analysis. Basically because they have Nick Trefethen, and several other very good people, many of which I know. So they really do numerical analysis at the very highest level. So I wonder what their grad students do if their undergrads do this. So, but in spite of being an undergrad textbook, I could definitely say this is more advanced than any of the books that I've used for 460, 461. It's unfortunate that they don't give problems involving coding, because I know at least some of you guys would prefer to deal with that. But I do have sample code out there for a lot of methods, so we can kind of work that in. Now, as for what the course is going to involve, so on the syllabus, you have the website address. It's very important to go there, especially any of you, I guess several of you have taken a class from me before. And you know how it works, where I have my lecture notes there, and that's really what I'll be going by. That's based loosely on the book. As far as how the grade is determined, what I find, if you look at the schedule and I'm pretty much going to stick to the schedule unless there's a hurricane. I do my best not to fall behind, or basically I just plow ahead, so you better keep up. But there's kind of some blank space at the end. So that gives me a little bit of leeway. And the way in which I like to use this leeway, and I pretty much only do it in this class because it's the only class where there's time for it, is to put you guys in the spot. Have you come to the board and work out a problem. Now you'll have some candidates as for which problems I call on someone. Also, and it's going to be, I would like rotate through you all. Of course, I've never had as many people in the class. We might only be able to, we wouldn't be able to go through all of you that many times. But so all the problems that you're going to have to deal with, except for the final exam, they're already posted on the site. So I have these homework assignments. I don't collect them, but those are problems I pick for calling on somebody. So if you're the last person to be called on, you can trust that you're safe for a while. And then we have some take-home exams, but those are also based on different problems in those same chapters. And those will be collected. So a big part of your grades from that. And then we'll have a plain old final exam. So during finals week in class. During the regular final exam time. Okay. And actually, I was hoping that for those of you who are PhD students, we could actually use that for a comprehensive exam, but we're not allowed to do that anymore. So a comprehensive exam has to be written and graded by 2 faculty members. So for this class, it would be like myself and Dr. Dane. We'll see how that goes.
When do you take them then? The comprehensive?
Well, they can still be taken pretty flexibly, because you just let us know what you want to take it, and then it's giving effect and there's time to write it. Now, since it's going to be like a team effort, I guess that slows down the exam writing process.
So can I not take it till I start my PhD?
Yeah, you can. Yeah.
Okay.
Yeah. Okay. Let's see. Anything else from the syllabus to deal with? Not really. So just the standard stuff. So it'd be a good idea, since you can see what I'm going to cover each day, but either look in the textbook or look in the notes to see if I have an idea. And then I'm still going to go through the whole thing here, but at least you can have a better chance of understanding it. Okay, so does anyone have any questions about how the course is to be run? And it's pretty plain vanilla here, so it's a material that's weird. So, okay. All right. So what I'm going to start with are, I'd like to start with some decent chalk. Okay. Because we're going to consider a number of problems during the semester. How do we solve nonlinear equations by iteration? That's the first one. Polynomial interpolation, or other forms of polynomial approximation by minimizing some form of the error. And then that paves the way for numerical differentiation integration. And then we'll finish with solving ODEs, initial value problems. Sometimes this course includes numerical linear algebra topics, but I don't cover those because we also have Math 610. That's offered that's going to be not every spring, but it's going to be offered this coming spring, where all that stuff can be covered in but before we get to nonlinear equations, we'll spend a little time talking about error analysis in a more general sense. Because in most of your math courses, you're accustomed to solving problems using analytical techniques, formulas and so forth, where you produce an exact answer. But in numerical analysis, we're looking for an approximate answer. That's all we can get. But then we can attack a wide variety of problems for which analytical techniques would be useless. Okay. Now, so the process, I'm going to describe, for solving a problem using a numerical method, I'm going to use really abstract terms here, but to introduce some important concepts that are applicable to all the problems that we'll be considering. So what we want to compute is some quantity y equals f of x, but this is a bit broader than just normal evaluation of a function that you're used to from our math classes. So all the entities here represent different things than what you're used to. So x refers to whatever input you have. And of course, y refers to the output. So that part isn't any different in a general sense. But then f, you can think of as some sort of algorithm that's meant to obtain the exact answer. So for instance, if so to give you an example, suppose the problem that you're trying to solve is ax equals b. So I know we're not covering linear systems in this course, but it's a simple example to describe what I'm talking about here. So then your input x refers to whatever information is given in the problem. So in this case, that would exist in two parts, the matrix A and the right-hand side vector B. So all of that is your input, whatever is handed to you. Your output is the exact solution x that satisfies this system of equations. And then your algorithm f would be any method that could be used to obtain the exact answer. So it could be, for instance, Gaussian elimination, which would certainly produce the exact result if you could perform exact arithmetic. Or there are also iterative methods. All this will be covered next semester in 610. However, one very important point is you're supposed to produce the exact answer. So if you're going to use an iterative method, then the number of iterations has to be literally infinity. But the point is, this is an idealized version of what you're trying to do. So you want the exact answer, but then error analysis is about a situation where the exact answer, for whatever reason, is unattainable. And you're settling for something less, and how bad is that situation? And there are other examples. For instance, if I'm solving, well, I'll give one more example. So, more relevant to what I'm talking about later today. F of x equals 0. You want to solve a nonlinear equation for some given function f. You want to find a root of that function. So the input is actually your function f. So you're handed this function f, and the problem is find a root of it. And then your output is some x value, x star, such that f of x star is exactly 0. And then your algorithm f, and I'll admit the unfortunate choice of notation here, but you're grad students, so deal with it, is any root finding method that you could use. In certain simple cases, it could be a method that produces the exact answer, such as if it's a quadratic function, you're using a quadratic formula. Or if it's not something easy like that to work with, maybe it's an iterative method run infinitely many times, etc. Okay, so this is what we're after. But now let's talk about what we have to settle for, because if it's not practical at all to obtain the exact answer. Okay. All right. Okay, so what we get instead is, if we see, in many cases we can still have our exact input, x. Not always. For instance, what if if you're solving a system of equations and one of your entries of your matrix is pi? We can't represent pi exactly in a computer, so there may be some error there. But in a lot of cases, your input can still be considered the exact input. But then, whatever algorithm you have that will give you the exact answer, you cannot use. So you have some approximate algorithm, something that is approximation of a process that you would like to use if you could, to get as close as you can to the exact answer, and then you're going to get some output y hat. So we're getting an approximation of a value f of x that you're after. So I'm going to use hats to refer to approximations here. All right. Now, so I'm going to use this notation to introduce certain terms of importance in error analysis. So we have absolute error is nothing more than the difference between your exact solution and your approximate solution. And often we want to quantify this by a single number, because this value y could be a vector quantity. But if we're trying to measure error, we get some sort of magnitude, like it could be absolute value, or it could be a norm of a vector, like for instance the Euclidean length of a vector. So there's some notion of magnitude involved. Okay. And then we also have the relative error. So that's going to be the absolute error divided by the magnitude of the exact value. So that way the error is expressed like a percentage, like if you're 1% off. And often the relative error can give a more meaningful indication as to how accurate your answer is. Because suppose you, if the exact value was on the order of 1,000,000, and your approximate answer was roughly like 1,000,001, your absolute error would be 1, which sounds bad. But your relative error is going to be like 10 to the minus 6. So in that case, you say, well, then you did a good job. You have a reasonably accurate approximation. So it all depends. Whereas if the exact value is near 0, or it's exactly 0, then the relative error is not a good indication. You should use absolute error. So either one can be a more reliable indicator of accuracy depending on the size of your exact answer. Okay. So any questions so far? All right, because what?
Excuse me. So you mean any of these that works well? Then we could say we could choose and say, okay, this is the error that work, and you're done.
I'm sorry, what?
So you said that for some cases we could get a very bad answer for
Oh, okay.
absolute error and a good result for the other one.
Yeah.
So,
But the thing is, most times it's relative error that's best to use, unless the magnitude of your exact value is small. Then relative error is kind of misleading, and absolute error is the best one to use. In fact, in my papers, for instance, I always use relative error. But that's because my exact values have a reasonable magnitude. But a lot of times, of course, we don't know why. So the best we can do is really try to estimate what these errors are. So in some cases, like in some of my research, I compute something that's very close to an exact solution just by some terribly inefficient method. Or I might make up a problem that's contrived in such a way that I can get the exact solution, and so then I have something to compare against, even though in general that cannot be done. So there's different ways of estimating this kind of error, but an estimate of the error is all we can hope for. But it's also all we need, because we just want to have some ballpark as to how the error behaves. But that takes me, I don't know if I answered your question.
Yeah.
Okay, any other question? Because things are about to get weird. So, because like some of these concepts you may have seen before, but this now we're crossing over into the dark side of error analysis. So, because of the trouble is, this is the error that we actually want, that we care about. We want to see how accurate our algorithms are producing some approximation of y. Unfortunately, this can be very difficult to do. Right. So, it can often be easier to estimate the error in a roundabout way. And that's what I'm going to talk about here. Using a concept called backward error analysis. Okay. Now, the idea behind backward error analysis is that we're making an assumption. And the assumption is that our approximate value, which is an approximate algorithm applied to the true input, can also be thought of as the exact algorithm applied to an erroneous input. So in other words, we're saying the approximate solution is the exact answer of a nearby problem. So the idea is this erroneous input is some approximation of a true input. And this is not something that always holds, but for certain problems, such as, like, for instance, systems with linear equations and so forth, it is a reasonable assumption to make. So that leads us to a different kind of error called backward error. So backward error, there's absolute and relative, but applied to x. So x minus x hat, or x minus x hat magnitude divided by the magnitude of x. So you have absolute and relative error in y and in x. And when we're talking about backward error, then the error in y, which is still what we care about the most, is then referred to as a forward error, just to distinguish. So now we have these two kinds of error, forward and backward error, and in each category we have absolute or relative. Okay. And this kind can be easier to estimate than to try to do forward error directly. And the thing is, suppose we can get an estimate, at least how big backward error can possibly be. How does that help us get the forward error? Because that still has to be our end result. And the way we do that is use what's called the condition number. Of our true algorithm f. So you can think of it as difference in f values. So we have an absolute condition number, which is now the thing is f of x and f of x hat is nothing more than our exact and approximate y values. Okay. So, but what does this represent? you have a change in f divided by a change in x, what is that? What do we call that?
What did you say?
It's a change in f divided by a change in x,
Rate of change.
also known as,
Rate of change.
which is also known as a, for general functions, and for slope it'd be slope if it was a line, but.
Are you talking about derivative?
Derivative?
Yes!
Oh.
Oh, I didn't hear you.
No, I didn't say it loudly.
Oh, okay.
I didn't want to be wrong. But I thought that's what
Knock
it
that off. Okay, yeah, so it's a derivative of f, except f refers to an algorithm. So it seems kind of weird to take a derivative of an algorithm, but depending on the problem you're solving, like the first one we're going to look at, finding roots, there actually is a way to describe it, which I'll get to shortly. But one thing that's important to point out here is because we're making this assumption from backward error analysis, the condition number is a property of a problem you are trying to solve, not the algorithm you're using to approximately solve it. Because you notice there's only f here. There's no f hat. So for instance, take systems of linear equations. Those are any problem, like if not just that specific one, any problem is well conditioned if the condition number is in some sense small. Now, what means small, that depends on the situation. And is ill-conditioned otherwise. So if the condition number is large. So if you can figure out, or at least estimate the condition number, and you can estimate the backward error, you can just multiply those and get the forward error. Because that's what the condition number is. It's a ratio of forward error to backward error. Now here I've defined, what I've written down here is the absolute condition number. But I can also define a relative condition number by dividing this by y and this by x of their magnitudes. So the point is, if you have a problem that is ill-conditioned,
What do we consider small?
okay, for instance, for linear systems, the condition number is at least 1. So that's the ideal situation of well-conditioned. And even if it's something like 10 or 100, that order of magnitude, that's pretty good. But when you start to get condition numbers like 10 to the 6 or 8 or whatever, or worse, that's ill-conditioned. You don't normally get a condition number less than 1. It can happen, but it's a fantasy.
Excuse me. So there isn't any definition for ill condition. We just compare it by the values.
A lot of it depends on, for instance, if you're solving problems on a computer, what precision is available to you. Because the more precision you have, the more of a tolerance you have for a high condition number. Because if you, for instance, if you are solving an ordinary, a typical computer that has double precision floating point numbers, so you have like 16 decimal digits of accuracy, tops. And you're dealing with a problem that its condition number is like 10 to the 16th. You have no more accuracy. Your problem is so badly conditioned you couldn't even solve it reliably. But if you are working in extended precision, where you have more digits of accuracy than that, then it's not a big deal. So it's very context dependent. And that's why we don't have a rigid definition of what is ill or well conditioned. But if in your situation your problem is ill conditioned, then that affects any algorithm you can use to solve it. In other words, you have a bad problem. Now, is the situation hopeless? No. There are things you can do. Sometimes you can try transforming a problem to make it better conditioned. But you do have more work to do, and so it takes more ingenuity to get an answer that you can trust. All right. any questions about this? Remember, a strange concept. And I'm going to narrow it down because now I'm about to talk about root finding, and then I can say what your algorithm F is, and actually give you a simple formula for a condition number. But okay, and at least I still haven't chewed up too much of my time yet. Okay. All right. This is the part I want to get to anyway. So when I record these lectures, in case you in a situation where you can't make it one day, I'll try to have this posted. I try to do it right after class, but I also have my other class, Map 280, to upload too. So I might delay a little bit, but certainly by the next day, it'll be up. Okay. All right, so get into root finding. So this is chapter 1 in the text, and it's also chapter 1 in my notes. So a problem we're trying to solve is finding a root of a given function f of x. Now, it's possible to talk about this problem where f is a function of single variable or or multivariable. In this class, we're just going to focus on the single variable case, but most of the methods that I talk about can be generalized. Okay. So for the solution, I'm going to refer to as x star. So this would be an exact root. Now, a function, of course, most functions that have roots, they have more than one. What we're doing here is we're interested in finding a root. And then, for instance, if it's a polynomial degree n, if we found a root, we can factor it out and then try to find more. But we're just dealing with one at a time here. Okay. Now, I'll talk about existence. Okay. So for that we have the intermediate value theorem from Calc 1. Which says that if your function f is continuous on a closed interval AB, then so for each value y that lies between f of a and f of b, then there exists some value c in the interval ab such that f of c is equal to y. So whatever f of a and f of b are, there's going to be, so f has to assume every value in between just by continuity. And it makes sense if the function is continuous, there's just no way around that. So for instance, here's f of a, here's f of b. Who knows how f will behave as long as it varies continuously between a and b. And whatever values are in between, and it could go outside of that range of once. It could hit certain intermediate values more than once, but every value in between, it has to hit at least once. And the continuity is essential for that. So what that means is, if f of a times f of b is a negative number, meaning at f of A and f of B have opposite signs. One's positive, one's negative. Then f has to have a root somewhere in between. Okay. In fact, that principle leads to a method called bisection. It's a simple but slow method for finding a root. That if you know that the function f changes sign on a given interval, you can just keep cutting it in half and narrowing it down as long as there continues to be a sign change until you get narrowed down so much that you've hit upon a root. Now, the root, whatever root you have, is you don't know if it's unique. So unfortunately, the intermediate value theorem doesn't tell you anything about that. It's only an existence result. And unfortunately, there's not much of a way to generalize the intermediate value theorem to higher dimensions. Okay. Now, there is another result that is about existence and uniqueness of a root. Okay. And to set this up, instead of just stating the actual results, I'll start with a simple case. All right. We have a simple case of a linear function, y equals mx plus b. Okay. Actually, I think I'm not going to write this in slope-intercept form. I can use point-slope form. Okay. So where's the root of this equation? So we would want y equal to 0. Okay, so let's go ahead and set y equal to 0. And x, so the x value where the root occurs, I'm going to call x star, like I did earlier. So I'm just going to use that notation throughout this chapter to refer to the true root. So what is the root going to be if we just go ahead and solve that?
X naught minus, X naught minus Y naught divided by M.
Yeah. Okay. Now, but what has to be true of M for this to be valid? Yeah, we need it to be non-zero. Now, let's suppose that M was 0. What kind of a line is that? All lines are straight.
Sorry.
If M is 0. Yeah, horizontal. I get to bust somebody in that every semester. It's so much fun.
That was fantastic.
So thank you for the setup.
Yeah.
I'll be
Okay.
here all semester.
Cool. All right. So provided that M is non-zero, in the case of a line, if there is a root at all, so for M not equal 0, the root is also unique. Now that's a simple case, but what if we have a more general function? We can somewhat we can somewhat generalize this statement. This leads to because if I go ahead and write this it's more of a function like y equals f of x. So in this case, f of x is equal to y naught plus m times x minus x naught. Now, we know that m is the slope, But what can we also call m in this case? Yes. You can speak louder. It's fine. Oh, it's going to be a fun semester. Yeah. But yes, in spite of what happened a few minutes ago, yes, by all means speak louder. Okay. Yeah, so this is the derivative. And that interpretation is helpful. And as I now go to see the more general result, and that is the inverse function theorem. Okay. So the inverse function theorem says that if I'll first state it in one dimension. That's mainly what we're just interested in. That if f derivative exists at a certain point x naught and it is non-zero, then we can say that the equation f of x is equal to y has a solution, and actually has a unique solution for any y near f of x naught. Okay. So at least we have, near this point x naught, we have existence and uniqueness of finding roots. Now, in line of such a well-behaved function, we have uniqueness of a root just in general. So it's a global result, but for more general function with a non-zero derivative, we have at least this local result. Now, this is for a one-dimensional case, a function f of only one variable. If f is a function of several variables, what I would say instead is the Jacobian matrix of f has to be invertible. So when you talk about functions of a single variable, root finding involves dividing by a derivative. If you're dealing with functions of several variables, you are talking about inverting a Jacobian matrix. So we need that to be invertible. Okay. Now, one thing that comes up, which can actually cause... Yes?
Could you please explain what you mean by Jacobian matrix?
Oh, a matrix consisting of all the first partial derivatives of f with respect to all of its variables. So basically, it's generalizing the notion of derivative to the multivariable case. So like dealing with vector fields, for instance. Okay. And as far as our root finding discussion is concerned, we're not actually going to get into that. But if you would take anything you learned here about single variable root finding and how it would generalize to multivariable, then that sort of concept would become important. Next year, I'll be spending a lot of time covering that in my upper class this semester. So maybe we can sit in there too. It's at noon. Okay. Now, one issue that can come up which causes trouble for numerical methods is if you have a root of your function f, and the derivative at that same point is also 0, then you say that f is degenerate. Actually, degeneracy only comes from a derivative. So it has nothing to do with the root itself, but if the derivative is 0 at a point, we call f a degenerate function. We also say that x star is a critical number of f, but to the root function we call it degenerate. And if both f and f prime are 0 at this point, we can say that x star is a double root of f. And you can generalize this. For instance, if a second derivative is also 0 at that point, then f is a triple root. If it was a polynomial, when you have a double root, you'd have x minus x star squared in the factorization. So you can see where the term double root or triple root or multiple root comes from. Okay. So this one keep in mind because certain methods that work very well when x star is just a simple root, so only f is 0, can fail or perform very poorly if x star is a double or multiple root. And it's because of this derivative being 0, which causes results like these to not apply. Okay. All right. Okay. Now, since I talked about conditioning in a general sense earlier, I want to talk about conditioning again, but specific to a root finding problem. Okay. So let's suppose that f is 1-to-1, and therefore is an invertible function. Near the true root. So in other words, we have the derivative being non-zero, so the function is well behaved. So we're not dealing with any degeneracy or double roots or any of that. Then, our general process, y equals f of x, so the problem of finding a root of a given function is this. Our output is our root, x star. Our input, we want to find where the function is equal to 0. So you think of our input as being 0, and we're trying to compute f inverse, because this is equivalent to the equation f of x star is equal to 0. So you can think of this as a process. So finding a root is kind of like a process of computing f inverse at a specific point, 0. But I need this assumption that f is 1-to-1 in order to be able to talk about f inverse. And we can use this to measure conditioning or sensitivity. Because what is a condition number? It's a derivative of your algorithm. It's a derivative, in this case, of f inverse. So, now the derivative of f inverse of x. Does anyone know, remember from Cal 1, what is the derivative of an inverse function? Yes. 1 over f prime, you just have to plug in f inverse of x. Okay. So what that means is the condition number for root finding, which is the absolute condition number, you can use 1 over absolute value of f prime at the root. Because in this case, our x value of interest is 0, but f inverse of 0 is the root. Yeah. And we'll use absolute value here because we care about the magnitude of the condition number. We don't really care about whether it's positive or negative. So how the derivative is behaving near a root gives us an excellent measure of sensitivity to the root finding problem. So if the derivative is small near the root, that means the condition number is going to be large. That's where we're going to have a harder time finding a root using numerical methods like the ones I'm going to cover. Whereas if the derivative is large, then the condition number is small and it's going to be better behaved. And in fact, what I can do is use graphs of both situations so that you can see why the problem is very different in these two cases. So first we'll look at the well-conditioned case. All right, so in the well-conditioned case, this is where we have the derivative is large. So the graph is very steep. All right, so it behaves something like that. So here we have the true root x star, and so what can happen here is, suppose we try to find a approximation of x star by trying to find a value of x where f is reasonably close to 0, because we're trying to find where it's exactly 0, but we have to settle for where it's approximately 0, because again, the exact answer is generally unattainable. So what can happen is, because of the steepness of a graph, I could pick a point where f of x is relatively large. This is nowhere near the x-axis really, but if you look at x versus x star, these are relatively close. So the error, which would be epsilon, is pretty small. So when it's well conditioned, I can find a point where f isn't really all that close to 0 and still have an excellent approximation of a root. Now let's contrast that with the ill-conditioned case. So this is where the derivative is small, so function is relatively flat. So something like this, almost a horizontal tangent here at the true root x star. So what can happen here is, if I try to find a point x where here f of x is pretty small, but because of the flatness of a function, the gap between these two, this error, which I'm denoting by epsilon, is actually quite large. So finding the x value where f is pretty tiny is not going to be good enough this time. So this is the difference between a well-conditioned and an ill-conditioned problem. Because if you're using some sort of iterative method, a good way to tell when to stop is when f of x is small. And you might think, oh, well, I have f of x being equal to 10 to the minus 6. I should be near a root, right? Wrong. Or whether that's true or not depends on the conditioning. So what you can do is you can estimate the derivative as you're getting closer and closer to root, and that can give you an idea. Oh, I'm looking at an ill-conditioned problem. I need to keep going if I want to really be close to a root. Okay. So for methods we'll see, ill-conditioned functions f of x can be quite troublesome. Is there any questions about well versus ill-conditioned? All right. So now, during the 18 minutes I have left, we'll get into, we're covering a few different methods. We'll get into the first one. And actually I have Monday to continue talking about it. So we're not behind yet, but give it time. Yeah, well, I guess if we're behind a fall, the less chance I can call you guys up. I shouldn't have said that, should I? Okay. All right. So first approach we'll look at is fixed point iteration. So in fixed point iteration, the equation you really want to solve, f of x equals 0, is transformed into equivalent equation of this form, x is equal to g of x. Okay. Now there are many ways to do that, and at some point later in this section I'll talk about how you can choose g. But for now we just know that it's perfectly easy to do. For example, you can choose the simplest choice, choose g of x equal to x minus some constant lambda times f of x, where the constant lambda is not 0. Because if you choose that, then you can guarantee that f of x equals 0 if and only if x equals g of x. And later we'll see, if you're going to choose a g of that form, what is a good choice of lambda. Because then you can develop a very simple algorithm for solving the second equation, x equals g of x. So the actual algorithm for fixed point iteration, I don't feel like running it twice, is you choose some initial guess. Let's call it x naught. And then, actually, I'm going to check my notation. Okay, I do use the letter K for this. So during each iteration, what you do is very simple. Your new x is simply g evaluated at the old x. So it's successive substitution. You just keep plugging in again and again. And then you need to do some check for convergence. For example, if a difference between two successive iterates is less than some specified tolerance, like maybe 10 to the minus 8 or something like that. So you're checking for when to stop, but otherwise you just keep going, keep plugging in, and hopefully it will converge. So the intent is that the limit as k goes to infinity of xk equals a root of f, which also satisfies the equation x equals g of x. Okay. All right. Now, we need to have some idea of when this works. So there's a few theorems I can state for that. All right, so first, let's talk existence. And for that we have what's called the Brouwer fixed point theorem. And what that states is, if your function g is continuous on a closed interval AB, and the function g maps the interval AB into itself. So in other words, if x is in the interval AB, then g of x also is in AB. See? So once you're stuck in the interval, you can't get out. So if that happens, then g has a fixed point x star in the interval AB. So in other words, x star is equal to g of x star. Okay, so a solution of this equation I call a fixed point. It's also called a stationary point. In fact, there are other names still, but I'm not remembering right now. Okay. So at least under that circumstance, which is not necessarily easy to prove, but in some cases you can, you know that there is a solution. All right.
Is there a difference in a fixed point and a root?
Fixed point and what?
Yeah, what's the difference in a fixed point and a root?
Oh, well, a fixed point of this equation, well, when you say a root, it's a root of f, so when it's a root, the y value has to be 0. For a fixed point, the function value has to equal itself. Yeah. But yeah, we're going back and forth between two equations, but yeah.
What did you say for fixed point?
For-
Has to equal itself?
Yeah, that the y value equals the x value. These sides have to match.
So, okay, so the function.
Okay. Now, okay, so at least we have an existence result, but it'd be nice to have a uniqueness result or some reason to believe that this iteration here will actually converge.
Where are the applications of the fixed point?
What?
Where are the applications of the fixed point?
Oh, well, basically, anytime you need to solve some sort of nonlinear equation, often you can reformulate the whatever equation you're trying to solve as a fixed point iteration, whether it's a function of one variable or several variables. Yeah, but there's so many situations where some sort of complicated equation needs to be solved. Now, method we'll talk about later, Newton's method, which is most often used for solving nonlinear equations, actually is a form of fixed point iteration. Okay. The nice thing about the fixed point iteration is it's very general. And so that can be, so it's a lot easier to analyze theoretically like we're doing here, and actually have some confidence that certain equations can be solved at all. Okay. Now, another theorem is very helpful. It's called the contraction mapping theorem. Okay. Now, I'm going to start with this, I don't write them again, the same assumption that we had for a Brouwer fixed point theorem. So, in other words, we're in a situation where we know a fixed point exists. G is continuous, G maps the interval AB into itself, and then I need to pile more assumptions on top of that. So if the assumptions for a Brouwer fixed point theorem hold, and we have that the difference between G values is bounded by a constant L times the difference in these X values, where the constant L is strictly between 0 and 1, and for any 2 points x, y in AB. Okay. So if all this holds, and when this is the case, we say that G is a contraction on the interval AB. Now, I should mention just this line right here about g of x minus g of y is less than or equal to L times x minus y. This is an important concept. Here we say G is I have to be careful about the spelling here because, yes, Lipschitz with a C. Well, it's more than that. I had a professor at Purdue whose last name was Lipschitz without the C.
Oh, boy.
Yeah. So G is Lipschitz continuous, and the number L is referred to as a Lipschitz constant. Now, Lipschitz continuity is like a stronger form of continuity. So any Lipschitz continuous function is continuous, not necessarily the other way around. So a function could be continuous on an interval, but fail to be Lipschitz continuous, because maybe there's no constant L that you can use to peg down this change in G values. Now, okay, so to be clear, is Lipschitz continuous if there is a constant L, any constant L for which this works. If on top of that, the constant is less than 1, that is when we call G a contraction. So what we need for this theorem is for G to be a contraction. So if it satisfies the assumptions for having a fixed point and it's a contraction, then a lot of good things happen. Then we say that G has a unique fixed point. In the interval AB, and even better, fixed point iteration is guaranteed to converge. And that's right, you can choose any x naught in this interval where you know that G is a contraction, has a fixed point. So you have a lot of leeway in how you can choose the initial guess, and you can trust that fixed point iteration is still going to converge. Okay. Now, I'm going to give I could formally prove this, but I can give you the main idea as to why this works. So I'm going to put proof in quotes. So if you look at the difference between xk plus 1, so your k plus first iterate, minus the true fixed point. Well, based on fixed point iteration, xk plus 1 is g of xk. X star is g of x star, because it's a fixed point. So you can always make that substitution, that's very important here. And now you can use the fact that G is Lipschitz continuous. So this is less than or equal to L times xk minus x star. So here we have a difference of x values equal to a difference of g values, but Lipschitz continuity lets us write that as in terms of a difference of x values again. So what this does is, this relates the new error to the previous error. And because L is less than 1, the error is guaranteed to decrease. So what I can do is I can repeatedly apply this. So I can say that the error after any number of iterations is less than or equal to L to the k times the initial error. But what's happening to L to the k as k goes to infinity? What do we know about L?
It's between 0 and 1, it's just getting smaller.
Yes, it's going to keep getting smaller and smaller. So the limit is 0. So the error has to go to 0. So in fact, it's Lipschitz continuous, but also having this Lipschitz constant less than 1 ensures that the error is going to go to 0. Okay. know that, okay, sorry, pages are all around here. Well, I'm almost out of time anyway, but. Okay. How much time do I have? Ooh, okay. Well, I'll make a quick statement, then I'll stop. If we know that G is differential, because right now we're not assuming that G has a derivative at all, but suppose it does. So G prime exists on AB, well, G of x minus G of y over x minus y is equal to G prime at some value c, or c is between x and y. What's the name of this theorem called? From Calculus 1.
Is that another value
Is that the
theorem?
predicate value theorem?
What?
Is the mean value?
Mean value theorem. Yeah. So mean value theorem. But the thing is, this quantity in absolute value is less than or equal to L, if under assumption of Lipschitz continuity. So that means that G prime is less than or equal to L on AB. So this gives us another form of a contraction mapping theorem. So in addition to all the other assumptions of a contraction mapping theorem, if I also know that G prime exists throughout the interval AB, so if there exists a constant L, where L is strictly less than 1, so G prime of x is less than or equal to L on the interval AB, then again the contraction mapping theorem, its conclusions apply. So, and all the other assumptions I still need, so I'm not forgetting those. So in that situation, we again have a unique fixed point, and fixed point iteration is guaranteed to converge for any initial guess within the interval. All right. Well, that has me out of time, but we're in good shape. Okay, so what I'll do is I will continue covering fixed point iteration on Monday.